During the second hour, we're going to have a Q&A session. And so during that time, we'll stop the recording and we'll allow anyone who would like to ask a question to come off mute and have their video turned on optionally. And during the entire time, we ask everyone is welcome to put questions in the chat. So during the entire presentations, please feel free to add your questions to the chat, and we will be happy to get to those during the Q&A. During the Q&A, you can also use the raise hand tool, and we'll call on you to ask a question. Okay, so first off, we're going to hear from Daniel Jacob. He's the leader of the Atmospheric Chemistry Modeling Group at Harvard, and he's the principal investigator for the integrated methane inversion. So Daniel, I'll pass it off to you.
Thank you very much, James. So today we're going to be presenting to you the integrated methane inversion, or IMI, which is a user-friendly cloud-based tool to quantify total methane emissions from satellite data. So I'm Daniel Jacob, I'm the PI for the IMI, and I will be giving you an introduction to that tool, and I'll be followed by Daniel Veron, who's the IMI co-PI, and then there will be several hands-on presentations from Lucas Estrella, who's the IMI lead developer, Melissa Sulprizio, the IMI software engineer, John Thomas, who's the Integral Earth lead developer, and we also have on hand Mira Nagaranjan, who's our Integral Earth business lead, and I'm very grateful to James East, who's an active IMI developer, for being our workshop moderator. Before I go on, I would like to acknowledge our collaborators in this. Kevin Bowman, Hannah Nesser at JPL, Bram Massakers at the Netherlands Institute of Space Research, or ESRON, Sabur Barre at the Environmental and Climate Change Canada, and also the funding that we are receiving from NASA, from ExxonMobil, from Harvard in particular through the Methane Initiative, and from AWS. So the motivation for the IMI is the growing satellite constellation of methane observations. So we have a number of instruments in space that can observe atmospheric methane by solar backscatter in the shortwave infrared, which gives you a total methane atmospheric column. There are two classes of instruments. The first one is what I call the total flux mappers, for example, TROPOMI, that will give you global mapping of methane with a pixel resolution of 1 to 10 kilometers and high precision, which means that you can measure total methane emissions anywhere around the globe. And then you have point source imagers, which have much lower precision, but much finer pixels. For example, GAGSat or EMET. And with those very fine pixels, they can detect and measure the emissions from individual large point sources. But they cannot detect the background methane emissions. And then intermediate between these two is MethaneSat that was launched earlier this year. The data will be coming out early next year. And it has intermediate size pixels. It has high precision, so it can measure both total emissions and large point sources in its targets, which are 200 by 200 kilometers square, but only for those targets. So we're going to focus a lot of a presentation on observations from TROPOMI, because this is an instrument from the European Space Agency that has been giving since 2018 global daily methane observations at pixel resolution of 5.5 by 7 kilometers square and very high precision. And ESRON is producing open access operational methane data that's available on the AWS cloud. And we at Harvard have been working to refine those observations by bringing in information from GOSAT through machine learning. This is work that was done by my PhD student, Nick Velasquez. What I'm showing you here is a global mapping of methane from TROPOMI. And what you see is that methane can't hide. And with TROPOMI, you can get very important insights on the global methane budget and what is driving the methane increase. But you can also have a very high level of regional detail that allows you to look at emissions from individual basins, from individual regions, from individual countries. And then if point sources are sufficiently large, then you can actually see them with CHOPOMI. But they have to be much bigger than, say, what a GHGSat could observe. Okay, now what CHOPOMI gives you is information on total methane emissions, and the IMI seeks to realize this potential through an inverse analysis, and I'll be talking about this. Now, this is very different from the products that are available on detecting and measuring individual point sources. And I'm illustrating this with a Permian Basin example, which will be a running example for much of our presentation. On the left is observations from CHOPOMI, and you see the enhancement over the basin. And on the right here is collection of individual point sources observed by different instruments. Now, the point sources are very important because they can deliver climate action. If you identify a very large point source, then you can shut it off. But they account for only a fraction of total methane emissions, and that fraction can be relatively small. And they also can be very intermittent. And so what we are focusing on with the IMI is quantifying the total methane emissions. And we're doing so at a resolution of 25 kilometers. And this is unique as opposed to products that deliver point source information. And it's useful for what purposes? Well, first one is for emission reporting at a basin, regional, or national scale. In this way, you can average over intermittent point source observations because you observe them every day, so you can see when they're on, when they're off. You can monitor emission trends, and you can attribute emissions to different sectors. Now, in order to convert the methane observations from satellite to actual emissions, we have to do some operation that we call an inversion. In an inversion, what we do is we start from a prior emission estimate, which will be a gridded bottom-up inventory, and then we use an atmospheric transport model to predict the concentrations on the basis of that bottom-up estimate. We then compare those predicted concentrations to observations from the satellite. And the difference then can be used to improve the estimate of emissions, but you also have to factor in the uncertainties associated with errors in the satellite observations and in the atmospheric transport model. So the operation that you have to do is a Bayesian optimization, and out of this, you will get what we call a posterior emission estimate that will improve on the prior bottom-up estimate objectively by adding information from the atmospheric observations. So the way this is actually done in the IMI is summarized here. So we have a library of bottom-up inventories, we have defaults, we have alternatives, and users can add their own. We use a geoscam atmospheric transport model driven by the NASA meteorological data, 25-kilometer resolution. We then compare the predicted concentrations with what we observe from CHOPOMI GOSAT, and we throw in information from point source imagers. We use boundary initial conditions from CHOPOMI in order to avoid errors associated with that. And then we do a Bayesian optimization, factoring errors in the emissions, in the boundary conditions, in the transport model, and in the satellite observations. And we do this with an analytical method, which is considered the gold standard for inverse analyses, because it provides you with a mathematically accurate solution for the posterior emission estimate, and also it gives you error characterization. So you get error statistics, you get information content. This is a very standard method. It's been used in atmospheric chemistry since the 1990s. It's a textbook method, as documented in this book that I wrote with Guy Brasseur. The implementation in the IMI is described in a paper by Daniel Veron, and it's backed up by a large number of peer-reviewed publications from our group and from our collaborators. We recently released IMI 2.0, which adds considerable capability to the original IMI, in particular a multi-scale inversion capability with an adaptive resolution of emissions that allows you to go uh, from the basing level up to the continental scale and all the way to global analysis if you so choose. We incorporate now information from point source observations. We enable continuous emission monitoring, so you can see how emissions vary from 1 week or 1 month to the next. We allow for log normal air probability distribution functions, which means that you can capture the high tail of emissions and a bunch of other things that you will hear about in subsequent presentations and that are documented in a paper by Lucas Estrada. I would say that we continue to actively develop the IMIs. This is a big activity in our group and in collaboration with JPL. We're integrating new satellite data sets, in particular Methane Sat and GAG-SAT. We're increasing resolution to 12 kilometer, and Daniel Veron will be talking about this. And then Hannah Nesser and Kevin Bowman at JPL are extending the capability to CO2, at which point it may be the integrated carbon inversion. So a very important aspect of the IMI is the ability for non-expert users to be able to exploit it. So we often hear from stakeholders that they really would like to use satellite observations to quantify emissions from a region of interest. They just don't know how to do it. Well, what we are doing is we have put the IMI on the cloud, taking advantage of the fact that we have a satellite data on the cloud, we have a geoscan model on the cloud, so that users only need to log into AWS, access an instance, and then run the complete workflow from a single configuration file. And you run the whole thing in that way. And this is where the name integrated comes from, for integrated methane inversion. And then you can use a notebook to analyze output on the cloud or on your own computers. This, of course, does require some technical ability. Now, you don't need to do this on the cloud. You don't need to do this on the cloud. You can also do this on your own cluster by downloading the IMI using a Docker container. This requires even more technical ability and computing resources. So one thing that we have been very active recently is trying to democratize access to the IMI with software as a service called Integral Earth, in which you don't have to go to AWS. You can access the IMI through a simple web user interface. You can get advice and quality control from our team. You can access some enriched output analysis tools, including interactive tools, and this requires no technical ability. And you're going to be hearing from these different capabilities in the subsequent presentations. I would like to finish by telling you very briefly about our vision for the IMI and Integral Earth. So we are committing to supporting and developing the IMI as an open source, user-friendly, cloud-based tool. This is very important for us because this is critical to have credibility, reproducibility, and referenceability for our results, in particular for stakeholder and climate policy applications. So what we are actively building right now is a grassroots research and applications community of folks using and developing the IMI. At the same time, we are developing Integral Earth as this SaaS for accessing the IMI. And the Integral Earth, which we call IE, is presently in beta testing, and it's free. While it's in beta testing, we have an allocation from AWS. You should contact us if you want to be a beta tester. We're going to have a public release version by the end of this calendar year, and we're still trying to figure out the best business model for Integral Earth. And we can maybe discuss this a little more in the Q&A, but if you're interested in supporting the IMI or Integral Earth, we would love to hear from you because we are still figuring out what the best approach for this should be. With this, thank you very much for your attention. I'm going to hand it off to Daniel Veron for his presentation.
Great, thanks, Danielle. Let me pull up my slides. All right, so here we go. Right, so thanks. I'll be talking today about the IMI's capabilities and some of its applications, try to give a broad overview. It's not meant to be an exhaustive list of capabilities, but In general, IMI users can quantify natural and anthropogenic emissions and their uncertainties for any region of interest, states, countries, continents, wetland regions, oil and gas basins, agricultural areas, cities, and in some cases even individual landfills, as we'll see later. Um, they can compare emission inventories and reports with satellite data, monitor emission trends and identify emission drivers, investigate the global methane budget, and so on, and all of this without needing expertise in inverse modeling or high performance computing. And so, as we saw in the previous presentation, how all of this works is through inverse analysis of Tropomi satellite observations. And of course, we're working to add new satellite observations from new missions as they become available as well. But the general idea is to improve on a prior estimate of emissions from a bottom-up inventory using Bayesian statistics. And so, I won't go through this whole plot again in detail, but we start with our 25-kilometer resolution prior estimate. We use our transport model to predict what Tropomi would observe in the atmosphere. We compare that with the actual observations through an inversion to infer an optimal posterior estimate. And as Danielle mentioned, we obtain this through an analytical solution with closed form error characterization. Now, in practice, the starting point for doing this with the IMI is what we call our preview feature. And so the IMI preview is a capability that we developed to allow users to get a sense of what their inversion will deliver before committing to running it on the cloud. Because as with anything on the cloud, using AWS CPUs, for example, comes at a cost. Our code is free, but AWS CPUs are not. And so we want users to be confident that their inversions are well configured before they commit to run them. So the way this works is the user starts by selecting a region and period of interest at 25-kilometer resolution. The preview delivers the Tropomi observations and the prior emission estimates to be used in the inversion. The example here is for a 1-month inversion for the Permian Basin, where we have 20,000 observations. The preview also serves up some useful diagnostics like the observation density and the shortwave albedo. It estimates the information content of the inversion through the degrees of freedom for signal, or DOFs. This is a measure of the number of pieces of information that the inversion can quantify based on the observations. And here the preview estimates 12 for this 1-month Permian inversion. If the user is satisfied with the configuration of the inversion through the preview, they can run the inversion with a single command to produce the posterior emission estimates, the posterior prior ratios, and so on, as well as the averaging kernel sensitivities. And this is a 2-dimensional representation of the information content. It shows where the inversion is most informed by the observations. So here for the Permian, we have lots of information where there are high emissions in the Delaware and Midland subbasins, and the final DOFs result is about 11, so comparing quite favorably to what the preview estimated in this example. Now, for the remainder of this presentation, I will show a variety of example applications of the IMI and some of its different capabilities. I'll start with some of my own work using IMI 2.0 for continuous emission monitoring, in particular, weekly consecutive inversions for U.S. oil and gas basins in Turkmenistan. The regions of interest are shown in these maps. Inset for each of them, I'm showing the number of 2-dimensional emission elements that are quantified in the inversions. This is also called the state vector of emissions. So for Turkmenistan, there are 350 elements. For the Haynesville Basin, there are 38. And then also shown is the number of Tropomi observations available per week as a mean and standard deviation, which ranges from about 600 for Haynesville to about 20,000 for Turkmenistan. And this is a sort of sample of what these weekly observations can look like for these different regions of interest. Now, an example of the output from this analysis for the Permian is shown here. So this is demonstrating the IMI capability to quantify oil and gas emissions and intensity trends. And it's using the IMI 2.0 Kalman filter feature for continuous monitoring. It's 5 years of weekly Permian emission estimates, 2019 through 2023, and that's shown up here on the right. We can see this really striking seasonal cycle in the posterior emissions, which we're still trying to understand. Interannually, the variability is much weaker. And in the meantime, production of gas in the Permian has been surging And so if you put these things together, you can see that the emission intensity or the emissions per unit production has been going down over time, but that trend is driven by increasing production, not decreasing emissions. And in the next presentation by Lucas Estrada, you'll see how we can do improved error characterization for this inversion domain by generating an ensemble of inverse estimates using different inversion parameters. This is some similar results for national emission monitoring for Turkmenistan. This work came out of a collaboration with the UN Environment Program International Methane Emissions Observatory to support some of their work in Turkmenistan. And this is now 4 years of weekly IMI 2.0 methane emission estimates, including a 2D representation of the emissions changing over time here on the right. This application also demonstrates how we can bring point source data to bear on the IMI. So this scatter plot, for example, is showing how our total methane emission estimates week to week in 2023 compare with sums of point source emissions detected by different point source data providers across the country. Now, we can do this kind of national scale emission quantification at larger scales. For example, for the contiguous United States, this is work now from Lucas Estrada's recent preprint in GMD journal. And so this is for 1 year of inversions for CONUS. We're starting with the EPA greenhouse gas inventory, gridded version 2. That's shown here. And then on the top right is a map of the annual average posterior prior scale factors to produce a better match between geoschem and tropomi. So the inversion wants to scale up emissions, for example, from Texas oil and gas production from the California Central Valley, and it wants to scale down emissions elsewhere. The bottom two plots are showing the information content as 2D averaging kernel sensitivities for 2 different months during this annual inversion period. And so we can track how the information content of the inversion changes over time in this framework to see where our estimates are most informed by the observations. And this is really a demonstration of how we can use the IMI to help improve greenhouse gas inventories. Lucas's work also demonstrates some other IMI capabilities. So, for example, sectoral disaggregation of the posterior estimates can be done from his work. We see that tropomi would suggest that livestock and oil and gas methane emissions in particular in CONUS should be scaled up to better match tropomi. And then also he was able to demonstrate quantification of natural emissions. So this is showing a seasonal offset between Lucas's posterior emission estimate that's in the solid black here and the prior estimate over time. And we can see that there's a seasonal wetland offset indicating that we can use this tool to test wetland process models as well. We can do similar work at larger scales. This is work now from James East, tiling the world with high-resolution inversion domains to quantify national emissions globally. James has integrated point source observations into his inversions to update the prior estimates. This is an example of what the posterior scale factors look like from an inversion. So this is the scale factors to be applied to the prior estimate to better match the tropomi observations at up to 25-kilometer resolution for James's Middle East domain. And we can see that indeed applying those scale factors in geoschem improves the match between the model and tropomi. Before the inversion, we have, for example, these large negative biases in Western Turkmenistan, and after the inversion, those have gone away. And all of this is to generate country-level sectoral prior and posterior emission estimates globally. We can actually do this at an even larger scale by running true global methane inversions. So this is now work from Megan He. It is at 2 by 2.5 degree resolution, optimizing global methane emissions and the methane sink OH, the hydroxyl radical, with IMI 2.0. On the top left here are Megan's prior emission estimates, and then the scale factors from an annual inversion for 2021. And lastly, I'll show, as Danielle mentioned in the previous presentation, this upcoming 12-kilometer resolution capability that's being developed by Xiaolin Wang. And so this is a new high-resolution inversion capability. She has been developing it and applying it to quantify urban methane emissions. And so the example here is for the Los Angeles metropolitan area. Xiaolin's done a 25-kilometer resolution inversion and then also a 12-kilometer resolution inversion. And you can see how much more spatial information is present in the higher resolution inversion. We can see in particular a correspondence between the posterior emission hotspots and the locations of large landfills and downstream gas facilities. And so with that, I'll stop and hand it off to Lucas to talk about how to run the IMI.
Okay. Let me just get rid of that. Okay. Thanks, Daniel. My name is Lucas Estrada. I'm a third-year PhD student in Danielle Jacobs' group at the Harvard Atmospheric Chemistry Modeling Group. And I'm going to be talking about actually running the IMI and the best practices we use for using the IMI. So this first section will include a little bit of technical information, but coming next we have John speaking, and that will be talking about integral Earth, which is the easiest way to make use of the IMI. So don't be scared off. So there's three ways that you can access the IMI. The first one is using your local cluster. So if you have local compute resources, you can download the IMI via the IMI Docker container. The only software requirement for doing this is having Docker installed on your system. And then you can run the IMI with all of its dependencies within that containerized environment. So, and get out your emissions result. The other way, and the way that we've kind of designed the IMI natively, is to use the AWS cloud. And so with the AWS cloud, you effectively create an account. You then create an IMI instance. And then on that IMI instance, the code is pre-installed. All of the dependencies are pre-installed. And it's simply updating a single text file with your configuration and then running the IMI. And you'll see a live demo of this by Melissa Sulprizio in a little bit. And then there's Integral Earth, which we've talked about a little bit, but it's a web-based user interface that we've developed, which effectively takes all of the technical knowledge out of running the IMI and creates a request for an inversion that then gets run on AWS through our web portal. So I'm going to be focusing on on number 2 on this list, so using the AWS cloud. And so the first thing to know about the IMI is that if you're looking to get started with it, we have very comprehensive documentation located at imi.readthedocs.io. This documentation walks you through how to set up an IMI instance on the cloud, how to create an AWS account, how to actually run the IMI. It also gives you advice on capabilities and the best and features that we have. And we also have information on frequently asked questions, as well as the best practices for using the IMI. So this is just an example of our quick start guide, which kind of walks you through how to launch an IMI instance. It has screenshots along the way to help you get set up. So if you're new to the IMI, I highly recommend using our comprehensive documentation to do so. And once you get to the step of actually being on your IMI instance, then the only necessary step is to configure the IMI for your region of interest or and your period of interest. So the IMI is designed to be very flexible, meaning that you can adjust where you're looking at and when you're looking at from that single configuration file. So you can customize your inversion domain as well as your period. You can also select the spatial resolution that you want to use, including using kind of multi-resolution for your emissions estimate if you so desire. You can also modify the inversion parameters, or you can use just the defaults. We try to set reasonable defaults for all of the configuration so that users, for the most part, shouldn't have to worry about it too much. But additionally, you can swap out the prior emissions that you want to use. So things are designed to be very flexible so that you can do a large amount of science using the IMI, and do so in a way that requires minimal updating of the actual code, and keep yourself within the actual configuration file. And so this is an example that Daniel Varon showed with the continuous monitoring capabilities of the IMI, which is an option, or you can do a single inversion where you effectively get the average emissions for that period of interest that you're looking at. So this is an example of the IMI configuration file. It's in YAML format, and so it's just a text file, and I've kind of I'm showing here some of the options that you can easily interact with. So up here we have the period of interest where you can update your start date, your end date. Down here we have your region of interest where you can update the area that you're looking at. So in this situation, you can just create a rectangular region of interest, but we also have options to have more complex shapes if you're interested in looking at, for example, a specific state or country, etc. And what types of observations you want to use, if you want to use a updated Tripomi product, or if you want to use water observations, whether you want to use the continuous monitoring mode, which is a Kalman filter. And then once you've set up and we have many more configuration options in the IMI configuration file, but this is just a small subset. But really at the most basic level, all you need to update is the start date, end date, and the region of interest. Once you have configured it to your desired configuration, you can then run the IMI with a single command. And with that, I'm going to pass it to Melissa for a IMI live demo. Always dangerous, but we trust her.
Thanks, Lucas. Let's see. Okay. So as Lucas mentioned, we do have a lot of great documentation on our Read the Docs site. Our quick start guide will walk you through step by step the details of how to run the IMI. So for the purpose of this demonstration and in the interest of time, I'll assume that we've already gone through setting up an AWS account, setting the proper S3 permissions for storing your data, and launching an instance on AWS with the IMI loaded. And that's exactly what I've done here in my terminal window. I've logged into an AWS instance. And in the home directory, I have the IMI code and software loaded. So to get started with the IMI, you simply navigate into the integrated methane inversion directory, and you'll see there a config.yaml configuration file that Lucas brought up before. And this has the configuration settings for your inversion, including a run name, which we recommend running each inversion, naming it something different so that you don't overwrite a previous inversion. As Lucas said, you can do start and end date. You can modify your period and region of interest. And all of these options are thoroughly documented on the Read the Docs page. Further down, you'll see a section for setup modules and run modules, and these are several logical switches that you can use to turn on and off the different components of the IMI. So to get started, we recommend using the out-of-the-box config.yaml file on AWS. We've thoroughly tested this file and make sure it runs from start to finish. So it's a great way to make sure that you can also reproduce running the IMI without error. We also recommend, before you run the full inversion, running a preview simulation. And this is done by this logical do preview is set to true. And so we will go ahead and do that using the default configurations. As Lucas said, the command is sbatch run IMI. And what that will do is that will tell AWS to start running the IMI simulation. In this case, it's just simply the preview. Now, the output of your IMI run will be placed into this IMI dir directory. And so IMI output directory. So in there, as you can see, you'll find different directories for each of the inversions that you've submitted. And I already submitted a demonstration preview so that we'd have some contents in the preview directory. And that will include PNG files like the ones I'm showing here and that have been previously shown in Daniel Varon's slides. So that will show you an estimate of what your prior emissions would look like, what Tropomi would see for methane concentrations for your region and your period of interest, the number of observations from the satellite, as well as a text file with some statistics on the information content expected, as well as an estimate of the cost to run your full inversion on AWS. Now, what we recommend doing with this preview output is tweaking your configurations to get the desired output that you're looking for. And once you're satisfied with that, well, I should mention, if you're not satisfied with that, you can rerun the preview over and over. It's very cheap to run. And then once you are happy with your settings, you can return to your configurations file, open the configuration file, and then set the remaining logicals in the setup and run section to true. And what that'll do is that'll run the IMI from start to finish and generate a visualization notebook to help you quickly investigate the results of your inversion. So what I have here is a pre-generated visualization notebook that was generated by the IMI. It's a Python notebook. It also saves out as an HTML file, and you can also save out the individual PNG images for easy display. But what this notebook includes is a summary, some useful graphics and tables summarizing the output of your inversion, including prior emissions, the posterior emission estimate, a breakdown by sector, the scaling that you would need to get to those posterior emissions based on the information from the satellite, and so on and so forth. So as you can see, with a little bit of technical know-how, it's not too difficult to run the IMI on AWS. We recommend giving it a try and reaching out to us if you have any difficulties or questions. And with that, I will hand it back to Lucas.
Lucas, you're muted.
Thanks. Okay. Thanks, Melissa. Appreciate that. All right. So going back to running the IMI. So now I want to talk about a few of the best practices for when you're using the IMI and for people who may already be using the IMI. So I'm going to walk through working with the IMI preview, reducing computational costs, generating an inversion ensemble, and evaluating the quality of the inversion. So first, working with the IMI preview, Daniel Varon kind of explained how this works a little bit, but I'm just going to run through it real quick. So effectively, the IMI preview is designed to be a low-cost way of estimating the expected quality of your inversion. So effectively, you update your configuration files with the settings that you want. And then as a first check, you run the IMI preview to look at the observations, see where you have observations, see where you don't have observations, look at the prior emissions, as well as see the estimated information content going into the inversion. If you have sufficiently high information content and you're confident that you're going to get a good result from your inversion, you can then proceed with the full inversion. However, if you don't, there are several options for improving the quality of your inversion. Including increasing the period of interest, which will give you more observations to use as an observational constraint in your inversion. You can adjust the error estimates to be higher or lower. You can also change the prior inventory. For example, if you have a prior emissions inventory that you think is better, that will improve the estimated information content going into your inversion. Additionally, the IMI preview gives you an expected cost for your inversion, and that is mainly determined by the number of state vector elements or the number of emissions elements that you're trying to optimize. And so if you're looking at a larger domain, say the whole contiguous US, you would expect to have a much higher cost than if you were looking at only the Permian. And so I'm going to talk a little bit about options for reducing that computational cost. So as I said, the state vector is a 2D emissions field, so a collection of 2D emissions fields that you're trying to optimize. So each of these little points here. And so we have a couple of options for reducing the computational cost of running the IMI. The one that we've developed for IMI 2.0 is a smart adaptive clustering mode, which allows you to use multi-resolution for running your inversion. The native resolution of the IMI is at 1/4 degree resolution, or roughly 25-kilometer resolution. But for the whole contiguous US, that's about 10,000 state vector elements. And that means that you have to run many, many simulations in order to calculate your posterior emissions. And it can be quite expensive when you have that many state vector elements. Ideally, we want to reduce the resolution in some areas that have weak emissions or have low observational constraints, while maintaining high resolution in other areas that have high observational constraints. And what I mean by observational constraints is have high observation density and have high prior emissions. And the IMI does this using a smart clustering algorithm. And this smart clustering algorithm takes into account 4 different features going into your inversion. It takes into account your native state vector. It takes into account the prior emissions, the observation density from tropomi, as well as point source emissions from a variety of sources, including SRON, Carbon Mapper, and IMEO. It then takes that information and clusters your state vector elements, so aggregates them in those areas that we don't think we can constrain very well, and maintains high resolution in areas where we think we can constrain them well. So over here, we have the resulting state vector. Areas in blue/green are in high resolution, and areas in yellow are in low resolution. So you can see in areas like the Permian, where we have very high observational density, we have everything in blue. So we're using relatively native resolution here. And then in areas that we cannot constrain very well, we have in yellow. And we can optimize the state vector size by running it through the IMI preview at multiple different resolutions. So this is on the x-axis, we have the number of state vector elements that we're using. And on the y-axis, we have the estimated DOFs, so how well we're able to constrain our emissions. And you can see that as we increase the number of state vector elements, we're getting higher information content, which is what we would expect. But at a certain point, we start to level off. And at that point, we really don't need higher resolution. And so that would be the point that you would specify in your inversion as your desired state vector size when we have a leveling off of information content. Okay, the next thing I want to talk about is correcting boundary conditions. So boundary conditions can be a significant problem when you're looking at when you're trying to do a regional inversion. And what I mean by the boundary conditions is that what's happening outside of our inversion domain, so outside of this box, because we have methane all around this area. And depending on the meteorology, it blows into our inversion domain and can then affect our results. And the IMI handles the boundary conditions coming in by using a smooth tropomi boundary condition archival set that we create. And we do this by using the tropomi observations outside of our domain and scaling up or down a global simulation to generate our boundary conditions on the basis of the average concentration seen by tropomi in that individual pixel. The second way that we use to reduce bias from the boundary conditions is to optimize the boundary conditions as part of the inversion. And what this means is that we add 4 additional state vector elements to our inversion so that the methane coming in, say from this western side, we are correcting it as it comes in based on the observations that we have in our inversion domain. And we do this for each domain edge, so north, south, east, and west. And then the third thing that we do to correct to correct the boundary conditions, the boundary conditions coming in, as well as emissions coming from non-local sources, is we have buffer elements. And so the area that we're actually specifying in this inversion is outlined in red here, the Permian Basin. But you can see that there's quite a bit of space surrounding this region. And this is what we call buffer elements. So here we have 8 buffer elements, and we're optimizing these buffer elements as part of the inversion as well. So we're scaling these areas up or down to account for non-local emissions to our Permian Basin region of interest. So if there's emissions over here, we would expect the inversion to scale it up so that it better matches reality, and then we have a better result coming into the region of interest that we are primarily targeting in the Permian Basin. And we generally recommend that you throw out the information gathered from these buffer elements because they're really just supposed to reduce bias. And you only should look at the area in here in your region of interest. Okay, and now I want to talk about inversion ensembles for error characterization of the IMI. So the IMI uses an analytical method, which does provide posterior error covariance matrices. However, these posterior error covariance matrices are only accurate if you know your prior errors as well as your observation errors, and you're regularizing them appropriately. So when you don't know those very well, there are still ways to gather uncertainty estimates on your inversion results. And the way we typically do that is by generating an inversion ensemble. And the IMI makes that particularly easy because this analytical method that we use allows for quick generation of an inversion ensemble with very low cost. And so with that inversion ensemble, you would vary your prior inventories, you would use observational subsets, you would try out different prior errors, different observational errors, and then you could see what the span of the range of estimates for your posterior emissions is. And by performing this inversion ensemble, you can then create error bounds on what your inversion estimate is on the basis of this ensemble. And finally, evaluating the quality of your inversion. So this is the IMI provides information on how to evaluate your inversion results in the visualization notebook that we provide. So effectively, what the IMI does as an assessment of how well the inversion is able to minimize or reduce the bias associated with the prior and Tropomi observation mismatch is it provides these plots. So on our left here, we have the prior simulation. So this has the prior inventory fed into a chemical transport model. And it's the mismatch between the observed atmosphere by Tropomi and the simulated atmosphere using that prior emissions. And ideally, what you see is that when we update our prior emissions to use our posterior emissions, you want to see whiter noise coming out of this mismatch. So this is using the posterior estimate fed into our chemical transport model, our atmospheric transport model, minus Tropomi. And you can see that we have much lower errors or much lower biases in our results. So in the Permian Basin, you can see that we have a much lower bias in the California Central Valley and really all over the map. And so this is, and then a summary statistic, we have a average bias of minus 0.24 ppb as opposed to minus 2.05 ppb here. And so this is the most basic check that you can do to just see, is my inversion actually optimizing my emissions in a way that makes sense? And that's, if you want to know more about the IMI, if you want to know how to run the IMI, we have these QR codes here for our documentation, for our research paper, and for the IMI 2.0 research paper. Both of these papers will really tell you more about the IMI's innards and how you can use them for your research. It'll give you a full summary of the different features and capabilities going into the IMI. And everyone should have these slides sent to you so you can click these links or use these QR codes. And with that, I'll pass it to John to talk about Integral Earth.
All right. Good morning, good afternoon, and good evening to all our lovely conference attendees. We realize that you guys are in a lot of different time zones, and we've been so gratified with the response we've seen for this conference. I'm excited to talk to you today. I'm John Thomas. I'm the lead developer on the Integral Earth project, which again is a web app that significantly simplifies using the IMI and retrieving accurate, reliable, and open source methane data. So, agenda for today, I'm going to talk about the need for Integral Earth, why we put so much time and effort into making this product. I'm going to walk you through a user workflow, so what a standard Integral Earth user might experience with their process of submitting an inversion. I'm going to walk through some use cases and examples of both the preview output and the full inversion output. And then just to wrap it up, talk about some future developments that we have in mind. So, first of all, why did we even make Integral Earth? Well, as we've heard, there's been an increased attention on methane as a pollutant in it's been targeted as a way to meet short-term climate goals. The reduction of methane has been shown to be particularly impactful in reducing overall global warming. And we have there's been a growing importance in using satellite data as kind of an objective third party to use in informing these quantifications of methane. But this interest that we've seen in methane has come from increasingly non-experts. And so there's been a need for products that quantify methane, but in a more accessible way. So these non-experts are either non-technical, they don't have a background in programming, or they don't have specific subject knowledge in atmospheric chemistry, but they still need a way to quantify methane. And as you've seen, the developers of the IMI have done their best to make the IMI easy to use, being through making the IMI running from a single configuration file, making sure all the defaults in that configuration file generally provide a pretty good result. But in general, it's a product that is a little unapproachable for a lot of people that are just dipping their toe into methane quantification. So that's why we built Integral Earth to again significantly simplify everything that you've heard so far from Melissa, from Lucas. We want to reduce the barriers of entry as much as possible into using the IMI. And that's our goal for Integral Earth, to democratize access to satellite data for methane quantification by non-experts, non-technical, non-subject matter holding people. So let's walk through what a typical user might experience when first using Integral Earth. Number one, a great starting step for a lot of websites, a sign up page. And after that, you'll be taken to a home page where you can read more about the IMI, about GeoSChem, about the things that actually drive Integral Earth, the things in the background, as well as an about page that gets a little more in depth. After that, when they're actually ready to submit an inversion request to AWS for running, they'll come to this form, which again replaces the existing configuration file that Melissa showed us in her demonstration. And like Lucas was saying, when it comes down to it, the things that are actually required to run the IMI successfully is like a run name, start and end date, and then a region of interest. So that's how I designed this form, to be as simple as possible for new users. There are a host of advanced settings for more in-depth customization available in advanced settings modal, which I'll show you. But we boiled it down to really what's necessary. So now I'll show you how to actually select a region of interest. And I came up with 4 methods for easily submitting these regions. Number one, which I think will be probably the most popular, is submission through an interactive web map. This is super simple. You just drag and drop a polygon or a rectangle and then submit via there. It shows you the estimated area in square kilometers, along with the estimated number of grid cells in a full resolution inversion of your selected resolution. So this is 25 kilometer resolution, which again, in the current version of the IMI is the lowest, sharpest resolution, soon to be increased to 12 kilometer resolution in IMI 3.0. The second method of submitting bounds or region of interest is submission via latitude, longitude. This is kind of similar to the first version, but if you have specific numbers that you need for your inversion, say you're trying to base it off of a study, you're trying to reproduce the results, this is just an option for that. Third option, we know we have a lot of users in different countries that might just want to press one button and get bounds of their country. So we just have a drop down with many countries of the world that we'll just submit the bounds via that. And then the fourth option is upload via shapefile. For those of you who don't know what shapefiles are, it's just an industry standard way to share geometry. Usually comes in 4 files. It's very popular in the industry. Here's the advanced settings modal. This is a place where you can set more customized options like resolution using a blended product of Tropomi and GoSat satellite observations. You can set the Kalman filter mode, which is the emissions over time mode. You can adjust the state vector settings or dig into the clustering option that we have that Lucas told us so well about. After you've set up all your configuration settings, you'll be taken to a simple review page that shows your bounds and some simple stats about your request. After that, you can view the status of your submitted runs via a run display dashboard. You can see where the region of interest you've selected is, along with all your configurations, and then the status. So I thought now would be a good time to talk about what actually goes on in the background of Integral Earth. Number one, the user submits a request to the website for their specified date range and region of interest, along with advanced settings. And then after that, it goes through some automatic validation just to make sure that the run has a higher success rate, that there's no funny business going along with different variables. As we said, there's a lot of variables. There's a lot of customization that can go on. So sometimes things don't play nicely. If the website automatically does flag that there will be something amiss with the inversion, it'll be sent to our team of experts at Harvard, where we can then consult with the user to ensure that the product that actually comes out of the IMI is what they want. After that, it's submitted to AWS, where the site automatically checks out the machine image, provisions EC2 instances, runs it, and stores the data. And then all that data is then returned to the user via a web dashboard. So let's talk about the actual products that will be displayed in the dashboard before I show you the dashboards. So number one will be a reference map, just showing you region of interest again. And then plots and statistics taken directly from the IMI. Again, we want to be as transparent as possible with what goes on in the IMI. So we provide bias and error characterization, the averaging kernel sensitivities, which are just, again, as Lucas said, an estimation of information content, and then the prior and posterior emissions. Also useful on the web dashboard is a sectoral breakdown of emissions in the prior and posterior. So if you have 1.2 teragrams of methane emissions, exactly how much is coming from each category. Things like oil and gas, wetlands, livestock, even termites. It gets that granular. And then for inversion submitted with the Kalman filter mode, which again is the emissions over time, there'll be a simple line chart of those emissions over the entire time period. So the two example cases I'm going to show today are a preview run, which again, we encourage all users to use before they jump into a full inversion. This will be of the Four Corners area. This will be a 2-month period last year. And just to illustrate the default, I used mostly default settings for this. The second full example will be of the Permian Basin. We've used that example a lot for good reason. There's a lot of emissions coming out of there. This will be a 4-month period in 2023, and we're using the time series mode, the Kalman filter mode, at 1-week intervals. So you'll be able to see the line chart of how the prior and posterior vary over time. And for this example, we used log normal errors, which ensures a positive emissions rate in the posterior, as well as balances out if you have a region with that has a lot of areas with very low or no emissions and then high emitters, it accounts for error statistics for those regions. So this is what users will see for the preview mode. This is the four corners region. It'll show the observation count, so the number of tropomi observations used to inform this emission estimate. The estimated cost, this is not an exact cost. We're working with an undergraduate currently to help make this cost estimate more specific, again, in the hopes of being as transparent as possible for how much this costs to run on our servers. It gives a prior estimate of emissions and then the expected DOFs. So again, Daniel gave us a definition of that, but it's just a one number estimate of the averaging kernel sensitivities. Now let's move on to the full dashboard. We're going to try a live demo of this. As again, Lucas has said, that never goes wrong. And so this is the full inversion dashboard. We'll see some statistics over here, the prior, posterior, DOFs, bias and RMSE, and along with super observations, which I didn't mention, but it's just a way that we group satellite observations that are of the same pixel. It just helps cut down on processing time. Got the reference map here, along with plots that may look familiar to you that are already provided by the IMI. Eventually, these will be fully interactive, as these plots at the bottom are, that show sectoral emissions and emissions over time. These are filterable, so if you only want to see a few categories of emissions, or if you want to come over here and you only want to see, say, period 6 to period 12, you can zoom in on there and then see what's going on specifically in that time range. These plots can be downloaded via here, and these statistics can be downloaded as a text file here. Okay, so we're so excited about the progress that we've made with Integral Earth so far, but we realized that we've got a long way to go. It's a fledgling product still. But here are a few of the development improvements that we hope to make in the coming months. Number one, which I think is a really exciting prospect, is automatic monitoring. So this is a hands-off method of using the IMI, using Integral Earth, where you say, okay, I have a region, let's stick with the four corners example. I know I will want methane estimates for the next year. So every week or month or whatever interval you want, give me methane estimation from those time periods, and it will build a suite of emissions similar to the Kalman filter or time series mode. So it will just automatically do that for you. It will automatically send jobs to AWS. So we're actually pretty close to that. So yeah. Another thing that would just improve transparency of the process is having more granular job status. Currently, the job status are pretty coarse. It lets the user know if the job is running, or if it has an error, or if it's completed successfully. We want to be as transparent as possible about all the stages that the inversion goes through, just so that you can know what's going on. It's a cool process. Also, the ability to have customized dashboards. We realize there's a lot of ways that methane data can be represented. So an option we want to have in the future is that customers with that custom data, we want to incorporate that data into Integral Earth to provide custom dashboards for them using the IMI and using their data. Currently, Integral Earth is in closed beta testing. Don't let that word closed scare you off. We would love, love, love for you to be involved and to beta test. As Danielle mentioned, we currently have some AWS credits that we can use to beta test this product. So if you want to be involved, please email integralearthteam@gmail.com. This will be a first come, first serve system. We don't know if we can incorporate all beta testers, but we'd love to work with you. And then sometime in the next, by the end of the year or early next year, will be the full public release of Integral Earth that will introduce a pricing model that will just be the cost of running the servers on AWS plus a small fee. So that does it for our presentations. Thank you so much for coming and being present for this. I see a lot of questions in chat, and we're really excited to get to those. But just as a reminder, the IMI is openly accessible on the AWS Marketplace. If you want to read some very well-written documentation, you can head over to imi.readthedocs.com. Visit our informational site at integratedmethaneinversion.github.io. Or if you have specific questions that perhaps we didn't have time to get to today, you can email integratedmethaneinversion@g.harvard.edu. And then if you have specific questions for members of the team, you can reach out to us at the following email addresses. And I will post these in the chat for your future reference. But without further ado, I will pass it back to James to start Q&A.
Thank you, John. And I'm going to stop the recording now.